All right, guys, in the last video, we talked about how TLC can relate to HPLC as far as method development goes. So if we want to process a lot of samples at one time to see how they're going to interact on a stationary phase and mobile phase, TLC might be an appropriate way for that, especially if I'm trying to create some type of situation where I'm picking a proper mobile phase, I'm picking a proper stationary phase in order for this separation to take place. Once I develop it on a plate, then I have a better idea of what's going to happen if I go over to an HPLC instrument. And then if I go over to an HPLC instrument, that's great. That's not a problem, not a big deal. This works for me if it works for you. And that gives me an idea of what I need to do for instrumentation settings. What I didn't get to talk about, though, is the idea of RFs and appropriate RFs. So we said that 0.2 to 0.8 is really kind of the realm that we like to run in when it concerns how these spots travel up the plate. How far do we like for them to go up? We don't want them to go to the tippity top. We want them to move from the bottom. So here in this kind of example, what they're showing you on this side, on the left side, is the normal phase. So normal phase is a hexane that's 80%. And they are developing this on multiple different types of stationary phases. So Si60, that is the traditional silica that we always use, that we always refer to. And then the NH2 is an OH group that's been modified with a amine group. And then the CN is a nitrile group. The RP2 is a 2-carbon group. The RP8 is an 8-carbon group. And the RP18 is an 18-carbon group. So we've modified the stationary phase along the course of the way. And we're just tracking to see what's happening to our spots. So here are the things that we have injected or that we have applied onto the plate. Again, very common all the way through. This basically was coming from our previous example that we talked about in a way. And then if we take a look, we get 3 spots that show up on the plate. That's great. They're separated, sure. If we calculated an RF, though, what we would see is that the spots down here at the bottom, those RFs are really not appropriate. And the reason is because they need to go to a 0.2 or higher. That is really where we like to be. So if we wanted to use the hexane acetone mobile phase at 80-20, and we don't want to change that, then if we run a normal silica plate, 2 of these are so low on the plate, we just don't feel comfortable. And then the other ones, you know, hey, we got a long way to go in order to get to 0.8. I mean, we can let these things kind of travel a little bit further if we want. That's not a big deal. Okay, well, what would happen if we change the stationary phase? Get rid of the silica and go more in the non-polar region. So we start with amine, that is going to be polar. Then we go to nitrile, which is not as polar. Then we go to RP2s, RP8s, and RP18s, which are getting more and more non-polar as we go. So what we're seeing is that in our very first step, we actually don't see any improvement at all with 2 of the compounds. And then the third one will go up a little bit further. That's great. Okay, we're getting further away from the 0.2. That's good. That's where it was, actually. If we go to the nitrile plate, well, our first 2 separate, and one of them breaks over the 0.2 threshold. That is good news. The third one, if I look up at the top, has not reached our 0.8 yet. So that's great. It's just that first band, and I really want to be appropriate, and I want that to be above a 0.2 RF here. So if I go to an RP2, now what happens is that my first component is above a 0.2, my second one is above a 0.2, my third one is above a 0.2, and they all are well below the 0.8 over here to the side. Great, good news. I can use that plate. My spots are a little closer together, but that's never what this has always been about. What this has been about is separation, absolutely. But it doesn't mean get it as separated as you can. That does not make any sense sometimes. We want the components separated from each other, but we also want the components in a working realm that is 0.2 to 0.8 as far as RFs go. And if that means that my components are going to be squeezed together a little bit more, but separation's still there, folks. Look at it. Separation's still there. They are not overlapping on top of each other. That's fine. Separation took place. But I'm now in the working threshold of where I need to be. All right, well, if I go to RP8, well, this is okay as far as 0.8 and 0.2s go. They work. The spots are closer together, but they still work. Out of the two choices, the RP2 is probably going to be a little bit better. They're further apart. And then look at RP18s. RP18s are still between R.8s and 0.2 for RFs. But those spots really didn't do too much of a difference. I mean, they're kind of the same as what they were with RP8s. One got a little bit further up, which means those two spots are a little closer together, which still means RP2 is probably a pretty good option here for me. Same story on the right-hand side. This is reverse phase. So now what they do is that they use acetone and water, which is very polar. That is reverse phase for silica. That is also reverse phase for HPLC. These are polar mobile phases. That is reverse phase. You're like, well, wait a minute. There was acetone in the other one. Yeah, there was. But hexane is 80%. That's the majority. Hexane is nonpolar. All right, so same story, silica NH2, modified silica all the way across. No way on earth is that first round going to be accepted. All of these travel with the mobile phase. All of the RFs don't make any sense at all. Sorry. My NH2 groups. No, sorry. Bad. Not going to work. Try again. All right, so we go to nitrile, C triple on N. 0.8, 0.2 is where it needs to be. All three of those actually work. If I go to RP2, absolutely, all three of those work. If I go to RP8s, well, okay, absolutely, all three of those work. Sure they do. If I go to RP18s, guess what? They work. It's getting really close to 0.2, but it's there. So the other four options that I see here, the C triple bond N, and then the carbon 2, carbon 8, and carbon 18, they could be appropriate. They are giving me the ideal RFs of 0.2 to 0.8. It's just a matter of picking out the option that now will separate those three things from each other as much as possible. So if I compare the C triple bond N and the R2, these seem a little bit closer for the C triple bond N. So it looks like between those two choices, the RP2 is going to beat out the C triple bond N. Then if I take a look at the RP2 and RP8, I look at the distances between these spots. It looks like RP8 gives me a little bit more distance between the spots than the RP2 does. So out of those two choices, the RP8 is probably going to do a better job for me. And then if I look at the RP18, it does look like that third one goes down a little bit lower. I get more separation by definition. The others really haven't been impacted in so much. And they still go 0.2 to 0.8. So, you know, RP18, which is pretty common actually, by the way, that will probably be my best route. My RP18 in this scenario gives me the RFs where they need to be, and it maximizes the separation between all of the three components that I have there. But notice also a take-home story here. Both of these could be ran on either or. You could choose normal phase to run them, or you could choose reverse phase to run them. That's not an issue. As long as you're picking out the right stationary phase, then you can get something to work based on what you have. That is not an issue. No one says that you can only pick one or the other. You can actually do both. You just need to figure out the right combination of stationary phase and mobile phase to make it work. That's really all that it's ever been about. All right, so a little bit of summary here before we end this video. The United States Pharmacopoeia, European Pharmacopoeia, they publish chapters in the pharmacopoeias that are going to tell us instructions on how to run HPTLC. So for the first time, they actually started including this method. And because of that, this method is going to become more and more popular over the course of the years. And this began in 2015 to 2017. So the monographs are constantly getting updated. The HPTLC technology is actually now part in the back of the USPNF, for instance, that we've been working out of in our CTC 115 course, if you've taken that. And that's good. That's great because, again, it's more technology. It's more instrumentation. Currently, they put a focus on herbal medications or dietary supplements. They've strayed away from a lot of the drugs. They wanted to kind of pinpoint one or the other. Dietary supplements had looser restrictions. So that's kind of the route that they did first. And those are the incorporations that they began to do first. And that's where most of the settings of the instrumentation are going to be found in the general chapters. You're going to find a lot of the information about dietary supplements and how to prep them in those general chapters. Everything from the plate on the dimensions that we need to input into the software and into the machines, you're going to find that in that general chapter that we are referring to in USP&F. So that's really a lot of this information this came from. Also, with these, you're going to be running an SST. SST means System Suitability Test. And this is the concept that you're running a standard, and that standard should be giving you a preferred result. And we know what this is going to be. So this standard has a documented RF. As long as you use the right stationary phase, as long as you use the right mobile phase, and you make it match, then your standard should match the trend of the data. No matter the room that you're working in, no matter the instrumentation that you're working with, this is a system suitability test. You are making sure the system is suitable for what you need. So system suitability is often in the very first lane, and that gives us an idea. This is what we're looking for. This is where it's getting applied. Absolutely, it's present. I see it. It is there. And then that way we feel a little bit better about the standards that we're running. We're feeling a little bit better about the samples that we're running. But that system suitability has got to be in place first. The system suitability is very often a USP standard, so very expensive, very pricey, but it is, super pure. It is going to be as clean as it's going to get, and you have the intention here of injecting or applying a totally legit, pure sample that has been identified as being pure onto the plate, so that way you can make these things match. The flow chart with our instrumentation, whether it's KMag or something else, is pretty similar. These systems are about $150,000 overall. That's kind of where these price tags are going to be kind of dancing in. That does include everything, though. So it does include the automated application system, your developing chamber, some type of derivatizing chamber. It's going to be an immersion or a spray chamber, whatever case that might be. Your scanner is going to be in there. Your visualizer, so you can take pictures and stuff, will be in there. And of course, the software that's going to happen in the very end. So very often, that's where these prices are going to hang out. Now, over time, different models are going to be made. Some of the older models are going to go cheaper. The newer models are going to bring in bells and whistles. They're going to go more expensive. But if you're looking for a system like this, that is what you're going to be expected to kind of fork out if you want one. Differences between TLC and HPTLC, folks, are all the same. They're all separating. They're all doing it on a plate. They're all doing it with gas phase, mobile phase, stationary phase. One is just more controlled than the other. So if you take a look at these, the principle here, planar chromatography, the same thing happens with our machine. It's a plate. Primary focus, it's just simplicity. You just want to know some identification purposes. This, though, is going to make it more reproducible, better separation, and you can quantify. The process for TLC regular plates, flexible. This one, highly standardized. It is what it is. You got to follow that. It has already been predetermined. You don't get a lot of choices. So really your power here is going to come into mobile phase and stationary phases. Methods are well defined with HPTLC. They have to be if you want them to be reproducible. The methods on the TLC side, if you're doing it by hand, you're limited. You're limited on what you can do with just a simple little TLC plate tank and a lid. Flexibility, you get none. That's it. You got to follow the method. You follow the SOP. You follow the plate application methods. You got to abide by the USP and so forth. But your flexibility for a TLC plate is very high. You choose little ones, you choose small ones, you choose different sizes. Folks, that's up on you. The target here, reliable. It might not be quick, but it's very reliable on instrumentation. Faster development, absolutely. But there's so many steps that go into this, it begins to eat away on the development time that you were saving if you just did it by hand. As far as data goes, HPTLC takes images, computerizes it, saves the images in the software, absolutely, calculates RFs, does quite a bit for you when the hand measurement's not quite. You're taking pictures with your cell phone. Samples and references here, it says they got to be side by side on the plate. On the instrumentation side, it says on the same or different plates. Oh, no, don't tell me this. It's not true. Good rule of thumb, still apply samples onto a plate. Still apply standards and samples onto the same plate. Plates here with hand, you get varies. HPTLC, you're going to do 10 by 20s. This is pretty standard, but that's how most of the instrumentation is made. The USP, NF, the EP, all of the pharmacopoeias are writing and incorporating these general information sections based on a 10 centimeter high plate. Most of the time it is 7 centimeters or 70 millimeter stop. Why do you go to 20? You don't need to go to 20 because the stopping point here is 7 or 70 millimeters. So don't be that person. Cost, very expensive, of course, for instrumentation. A couple of troubleshooting things I want to do in this last video. Number one, if you see streaks and not spots, if you were hand doing them, you probably added too much. So dilute the sample and apply again. Sometimes the sample has too many components. It's not going to be appropriate separation. So change a stationary phase, change a mobile phase, try again. If you run and you get an upward crescent, so an upward crescent is the idea of like this, right? These are very strong acid or base groups that you are probably dealing with. You need to pH control these a little bit more. Some might be acidic, some might not be acidic, and they're going to go together as a group because for the most part they're the same, but some of them are going to carry some charges, and you start to see weird things that begin to happen in banding and in spot shape. So you don't want to do that. If it's too acidic, most of the time you add acetic acid, which is a weak acid, vinegar. I mean, you know, very safe to use. If it's too basic. If it's too acidic, then you're going to be using ammonium hydroxide. And again, a very common base, ammonia. You can get that in the store. You can get that, you know, super weak cleaning agent. So you can control pHs this way in a very safe way. But those are the two that are constantly used, I think, for the most part, for all the methods that I've seen at least, for an upward crescent. If you get a downward crescent, so it goes in the opposite direction, then that means that your silica was probably messed up, and there's moments where the silica wasn't fully interacting the appropriate way, and it created this downward shape or downward crescent that you saw when that sample was concerned. Your solvent line at the top, let's say that that line was crooked. What could have happened? So it went like that. Well, that means absorbent problems. So maybe you didn't check the silica. Maybe some stuff was flaked off. Maybe some surface damage had happened. So things are going to act in a different way, and you get a different line in the mobile phase areas of those things because it is affecting the way samples are traveling through, but it's also affecting the way that the mobile phase is traveling through too. On the edges, if you see some curvature that happens there, that means the edges were probably damaged or touched or flaked in some form or in some phases. So that's kind of what happens and why those solvents go crooked sometimes at the very top. Random spots, that just means that you were filthy and dirty, folks. You dirty, filthy animals. That's what that is. So as you were spotting, you were careless with your capillary tube. Stuff was dripping on the surface of the plates. And as you were spotting down at the bottom, you were probably moving across the top part of the plate. Stuff was dripping and you had no clue that it was dripping. And then you were spotting it too all at the same time. So splashes were happening everywhere, or maybe you handling it it with no gloves contaminated as well, and added extra things that are showing up with the derivatizing agents that you were putting onto those plates, and you don't want to see that either. No spots that were seen. A couple of things could happen here. Maybe you didn't spot enough, because it does take a certain amount for it to show up on a visualizer. So maybe you need to go back and add more sample. Maybe the components that you were looking for did not respond to UV. We have already talked about that. It's not universal. It doesn't work for everything. So you need to try another detection method to see if that actually shows up. If you accidentally used a plate that did not have the UV 254 indicator on it, it's not going to show up as 254. You're not going to see anything at all. And believe it or not, some of the people that I know of personally have used plates that do not have that 254 on there. And then next was the solvent level deeper than the origin. So things did not migrate up. What happened here is that things soaked out, and things soaked into the developing solvent, and then they went throughout the entire developing solvent, and then it all went up the plate, and now it's so weak that you can't see it. Or it was strong and it's still strong, and now it's contaminated the entire plate and you still can't see nothing because it looks like one big old blobby color. So again, problems. So you know as good as well as I do, on the test, on the quizzes, I'm going to ask a little bit about troubleshooting. What could have happened to make these product situations kind of be a thing? And how would you go back and how would you fix them? All right, so folks, that's going to end our lecture on HPTLC and TLC. It includes the high-performance thin layer chromatography instrument. It also gives you a general overview of the proper ways that we should be developing plates and what we should be doing and what we should not be doing by hand, as well as a little bit of automation or instrumentation added to it. So hopefully this opened up your world a little bit to TLC. Some people have seen this before in previous classes. They probably have experienced it with a coffee filter, or maybe a piece of filter paper, something simple, maybe a microscope slide plate. But this goes well and beyond what you have maybe encountered up to this point. And I think that's good, because that's the point of taking a chromatography course like this one. So now we get a little bit better feeling of what's out there. We can quantify, we can give TLC its respect that it deserves, and we can do way more on it now than what we could before. So with that said, good luck on all the Canvas assignments. Good luck on all the online stuff. I'll see you in the lab, and in the lab we'll be doing a handful of these different TLC types of separations. And we'll kind of change it up depending on what the lab is. So that way we can feature, maybe derivatization one time, or maybe a two-step derivatization or a two-step analysis on one of the options. But we'll at least change it up and give you a flavor of how all of these things are going to be. So good luck. If you got questions, let me know. And otherwise, folks, I'll see you in the lab. Lab ready. Lab coat, safety glasses on.